and also K-means last week, right? We covered the basics of clustering and the advantages and disadvantages of K-means. We covered the outliers. So if the first disadvantage of K-means was that when we have outliers, the outliers can actually drag the clusters in one or the other direction, and it can just ruin our results. And the way to fix it was what? How do we fix it? How do we handle the outliers? Of course, we can use trimming, or we can use the other methods like Windsorizing, trimming, Windsorizing, other methods to handle outliers. But there is also another way, and that is having additional clusters. If we have more clusters than needed, the additional clusters can just cover the outliers and isolate the outliers from the rest of the data, so our data is not affected by the outliers. Therefore, we handled outliers. The other disadvantage was that the final solution is sensitive to the initial points or the initial conditions. For example, if we start with two centroids that are up and down here, the result would be clusters that are like this, up and down. But if we start with the points with the centroids that are left and right, the final result will be clusters that are on the left and right, like this. So which one is better? Which one is the correct answer? Which one is the optimal answer? To answer that, we have to understand the meaning of distortion. Distortion is an important measure of efficiency or optimality of the final solution of clustering methods. First, we define W of each cluster. W of each cluster is the sum of the squared distances from the centroid of the cluster to all the data points inside that cluster. Therefore, we call it within cluster sum of the squares. Within cluster sum of the squares is W. And it's like this, you have these data points and these data points here, and then you have two clusters. Each cluster has a centroid. Of course, we are talking about the final solution. The centroid is the mean point or the center of gravity of all the data points in that cluster. So far, so good. What is W1 or W of the first cluster? It is sum of all the distances squared. Sum of all the distances squared. So the distances between the centroid of the cluster and the data points in the cluster, all the distances squared. So sum of all the distances, and get within cluster sum of the squares, or W. This is W1 or W of C1, and this is W of C2 or W2. And we have that. Now that we have within cluster sum of the squares, we can define something very important. WSS. WSS, or within cluster sums of squares, is the sum of W's. The sum of W's. The sum of W's across clusters. So if we have like 10 clusters, it will be sum of 10 W's. If we have 2 clusters, it will be sum of 2 W's. So within cluster sums of squares is the sum of within cluster sum of squares for each cluster. Is that clear? Essentially, we add up sum of squares within each cluster. And you don't need to worry about the between cluster sum of squares, which is about the distances between the clusters. We don't need that measure in our analysis. But now what can we do with WSS? What we can do is that we can simply use it to decide which final solution is the better one, which final solution is optimal when we start from different starting points, different initial conditions. Okay, so the initial condition that has WSS of that has a larger WSS is the better one, right? The initial condition that results in a larger WSS or the final solution that has a larger WSS is the better one, right? Right? Are we good? No. The smaller one is the better one. The smallest WSS is the better one. We want WSS that is small. The smallest WSS means the most efficient cluster. Because we want to be closer to the centroid. We want the data points to be closer to the centroid. Okay. Larger distances are worse. All right, we handled that problem too. A problem with different final solutions and having different final solutions based on different initial conditions. Now, the last problem with K-means, the number of clusters. We have to specify the number of clusters. So what is the optimal number of clusters? That's a very important question. What should be K? To answer that problem, again, we will refer to WSS. Let's start with this example. Let's start with one cluster. When we have one cluster, the sum of distances would be the largest. Keep in mind that WSS has always the same number of Ds because we have the same number of data points, right? The distances can be to one centroid, two centroids, three centroids. Still, we have the same number of data points. They can be distributed in 2 clusters or 10 clusters. The number of data points is the same. Okay. Now, when we have one cluster, all the data points are in one cluster, and it has a very large W. When we have 2 clusters, there are 2 Ws. One of them is a small, one of them is larger. The sum of them is smaller than before. Then we have 3. The sum of them is even smaller. And as we increase the number of clusters, the WSS decreases, inevitably decreases, right? Because as we have more centroids, the distances from the data points to their centroids, the sum of distances from the data points to the centroids will decrease, inevitably. So that's like this. You see? We have one cluster, this is WSS, then this is WSS, then this, and it decreases. What is the optimal number of clusters? We use the elbow rule. Based on the elbow rule or elbow method, the point at which the slope of the diagram changes sharply or changes the most, that's where we have the optimal number of clusters. because you see here, we have a sharp decline in WSS when we increase the number of clusters from 1 to 2. When we increase the number of clusters from 2 to 3, again, we have a sharp decline. However, when we increase the number of clusters from 3 to 4, it's not a sharp decline anymore. It's a very smooth decline. See? So here, the slope changed from a sharp decline to a slow decrease. So this is the point that we call it the elbow point. And you see the point that the diagram breaks, kind of. That's the optimal number of clusters. For example, here, then we have one cluster. Here we have two clusters. That's WSS. We have 3 clusters. This is WSS. And obviously, this is the optimal number of clusters. Therefore, we handled that problem as well. So the optimal number of clusters can be specified just using the elbow rule. Okay. Now let's see how that works in R. Go to R. First, I change the working directory. Then I read this data set, scores.csv, has 100 data points. There are 100 students with the grades. 2 grades are important, previous grade and current grade, or the latest grade. 2 columns, 2 variables. And then we are gonna see the grades with respect to each other in a scatter plot. We're gonna have a scatter plot. Let's see what it looks like. Here we have 2 grades, the latest grade and the previous grade. And these are the students with their grades. Now we limit our data to these 2 columns because we are just focused on these 2 variables. Scores data gives us the scores of the students, just the grades. And then we scale the data. You know, when we have different variables, each variable can have different variances and different ranges. And when each variable can have a different variance, different range, what happens is that the distances can be heavily affected by the variable that has the largest scale. Therefore, we have to scale the variables so they are in a level playing field. Okay. So we just use the scale command to scale the variables. Now we have the scaled variables. Now we want to do the k-means. First, install these packages. And we use this package. Now, we can use this command, f is nb classed. This is a command for the elbow diagram. The first parameter is the scale data. You give it the scale data, and this is the first parameter. The second parameter is the technique that you want to use, k-means. You want to use k-means. And the last parameter is the variable of interest when we are optimizing, and that is WSS. Okay. Now I run it, and the result would be should be the elbow diagram. Something is wrong. Worked the last section, but let's try again. Okay, it worked. This is the elbow diagram for this data set. See, as you can see, as the number of clusters increases, the WSS decreases, right? And it seems to me that 3 would be a good elbow point. Now, a very important question, worth a lot of bonus. Actually worth full bonus. Full bonus. What is the minimum for WSS? And at what point we reach that minimum? As we increase the number of clusters, WSS decreases. It goes down and down and down. When we increase the number of clusters, it goes down and down and down. What is the minimum for WSS? And at what point it reaches that? And why 10? Oh, in this diagram, we just showed 10, but we could just go forward.
Oh, I didn't know. It was continuous.
Yeah, it is not continuous, but it can go forward. You know, it is discrete, but 11, 12, you can just, you can extend. You can have as many clusters as you want, but at some point it reaches the minimum. What is the minimum for WSS? And at what point it reaches that? Go ahead. 0, why? Exactly, that is correct. What is your name? Chelsea. I think I have it. Okay. So that is exactly the correct answer. So when we increase the number of clusters, at some point we reach the number of clusters would be equal to the number of data points, like here. So, and then each data point would become a centroid. And the distance from the centroid to the data point, of course, would be 0, because the centroid would fall on the data point. Okay, so these would be 0, sigma of this would be 0, and then sigma of values would be sigma of zeros. It would be sigma of zeros. Okay, that means we have as many clusters as the data points. Of course, it is not much useful, but that's the minimum for WSS. Good, good job. Now here, I think 3 clusters would be very reasonable. Now let's run the k-means command, k-means function, to get the results for 3 clusters. In this function, the first parameter is the data, the 2 variables that we chose. The second parameter is the number of clusters or centers, k. And then the last parameter is the number of starting points, 100. And that's because, as I mentioned, the initial points matter sometimes. What it does is that it starts from 100 random points or 100 random sets of centroids and compares the WSS for the different solutions, for the different outcomes, and it takes the outcome with minimum WSS as the final solution. Let's run it. When we run, it puts the output for the results in data frame KM. This data frame has all the results of K-means. The clusters, the centers, within SS, everything. Within SS is W. And we have the W's here. It is a list of W's within sum of squares. And we can sum them up to get WSS. Sum of within SS would be, so sum of these would be WSS. And yeah, let's see what it looks like in the diagram. WSS for 3 should be 87 something. That's here, 87. See, it's WSS. Matches what we see in the diagram. Now let's see the students in the clusters. I have the clusters here. KM $ cluster would give us the cluster for each record. I bind the scores with the clusters, but I bind the students with the clusters and attach the list to the list of students to see the students with their clusters. Here we have the students with their clusters. The first student is in cluster 1, the second is 1, the third student is in cluster 2. See? We can sort them out if you want, order based on cluster. And you can just put the students in clusters or see the students in order. So these students are in cluster 1, these students are in cluster 2, these students are in cluster 3. Now, so far so good. You could use k-means command, the k-means function, get the clusters. And now I'm going to show you one last command, FB's cluster. This command visualizes the clustering results. The clustering results are in KM. The KM data frame has all the clustering results. You should give it the data as well, the data points, the observations, and there are some other parameters just for visual purposes. And when you run this command, you see the clustering results visually. And where the students are in cluster red, green students are in this cluster, the blue students are in this cluster. And this is the visualization of the clusters. Any question? So on Wednesday, we could do the random forest, or we could just work on the team project. Which one do you prefer? The team project.